Welcome back, class. Welcome back. So in this video, we're going to discuss the dependent sample t-test or paired sample t-test as you would do it if you were doing your research project. Okay? So before we actually grab the t-test, I know it's in your textbook and I know they say you can do this or do that. You really shouldn't do the test unless several assumptions have been made and have been satisfied. If they're not satisfied, depending on which assumption it is, you may be able to violate the assumption and be okay, depending on which one it is. Specifically, normality can be violated and you still pretty much are okay. But there are other assumptions that if this is the case, you should look at using a different type of test to test the difference. Like, for instance, McNemar's test. That's one of those tests that you could use that's kind of non-parametric. Okay? So here's this basic setup. I have a group, and the group is size n. Okay, I collect data from this group before, some time elapsed, and I take some more data from them afterwards. So you have two sets of groups, right? You have the before data and you have the after data. So, and of course the data itself, when you think about it, is continuous. Okay? So the first assumption is that the dependent variable is continuous. In this case, when we say dependent variable, we're talking about whatever it is I'm measuring. Let's say I'm measuring, an example in the last one was jumping jacks or weight or whatever. Okay? And just to remind you, a continuous data set is one, or a continuous variable is one that's measured on the interval or ratio scale. Okay? So basically, it's numerical data. Secondly, there has to be two groups. Okay? Two, not three, two. And the groups have to be matched. Like a before group and an after group are matched because each of the people show up in each of those groups. Okay? So we have matched groups, two of them, not one, but two. And then here's the third one that we really don't stress as much as we should, but there shouldn't be any significant outliers in the differences between the two groups. Okay? So that means I have to take the differences first and then check for outliers on that particular variable. If you have outliers there, that has the tendency to make your standard deviation large, which, as we know, if you have a large number in the denominator, it's going to make your t-value small, which means you will not have enough power to find a significant finding. Hint, hint, throw in some of those words from today about power specifically. And the fourth assumption is that the difference in the dependent variable is approximately normally distributed. Now, there's a number of ways we can go about showing that, but like I said, it's relatively robust to this violation. So even if the dependent variable is not normal, you should be okay. But I'm going to give you about 4 or 5 ways to look at number 4 when we get to it. But just to start off, I have an example for you. Okay? At a recent PGA tournament, the following scores were posted for 8 randomly selected golfers for 2 consecutive days. At alpha equals 0.05, is there evidence of a difference in mean scores for the 2 days? Okay? So the first thing you have to realize is that I'm looking at the same golfer on Thursday and Friday. So I don't have 2 independent pieces of groups. I have the same groups that I'm following over time. So this is a dependent sample or a paired sample t-test is what we want to use. Okay? And so we have their scores over the last several weeks or several days. Okay? You may be tempted to find the average score and then find the difference and see what that's and use that number. But that statistic is not the one we need for the dependent sample t-test. Okay? What we need is the mean of the difference, not the difference of the means. But before we worry about the actual test, let's see how we do on our assumptions. So assumption number 1 is that the data has to be numerical. Okay, these are count data because I'm finding how many shots it took to finish my round, right? So they are in fact continuous data, discrete count data. Secondly, I have to have a group, okay, in its categorical group. In this case, it's Thursday and Friday were my groups, so I have a group of scores for Thursday and a group of scores for Friday. So far, so good. And the second one is, the third one says no significant outliers in the differences between the two groups. So in order to do that, what I should do, or what I could do, is actually calculate the difference in the scores, and then look at the z-scores, and then see if any of them are greater than 3 in absolute value. So at this point, I'm going to pull up my SPSS, because I don't want to do it by hand, and you shouldn't either. Okay? And I'm going to calculate the difference between Friday and Thursday. The way you calculate a new variable is to go to data, transform actually. This is one of the few times we'll actually use transform in our class. But under transform, you see there's a compute variable. Okay? And it's going to give you this formula. Okay? Under target variable is the name of your new variable. And I'm just going to call this diff for difference. Okay? And what I want to do is just calculate the difference. So I'll take this value, which is Friday, which is my last day, and subtract off Thursday. So it's basically final minus initial. Okay? You don't have to worry about any of this other stuff. We're not putting any special filters on it. I just want you to tell me the difference between Friday and Thursday. When I click OK, what you'll see back in your data file is this new variable called diff. Okay? I just don't like the decimal places. I'm just getting rid of them just because I can and I want to. Okay? And so you see 68 minus 67 is 1, 70 minus 65 is 5. That variable has the difference value. Okay? Now from this point I have to find the standardized value of the difference. Okay? So remember we went to analyze, descriptive statistics, descriptives, and you check this box that says save standardized values, and I want to save the ones from diff, and click OK. And what you'll see in that same box next to your diff scores are your z-scores. Okay? And a pretty cursory look here shows that none of them are more than 3 standard deviations away from the mean. So it's safe to say there are no significant outliers in the difference between the two groups. Okay? So we just looked at the z-scores, nothing different. The final assumption is that the difference is approximately normal. Okay? So there were a number of ways we looked at normal before. The easiest, okay, and the most low-tech way is to graph it. Right? So let's just graph it and see what it looks like. So if I did the frequency, and I'm not going to put the frequency table on, but I know I turned off everything, but I'm going to put diff on, and I'm going to grab my chart, and I'm going to grab the histogram, and show normal curve. Okay? So if my graph looks something like the normal curve, then I might think I'm okay. And then I click OK. So this is the histogram of that z-diff score. Mind you, I only have 8, so it may not look as normal as it does. But you know what? In all honesty, it doesn't look too bad. I mean, I have one little box there that's missing, so that means I kind of tilt most of my density to the left. But in terms of how many, it looks pretty good. So I would say, yeah, it's kind of approximately normal. You know, this might be one way to do it. Another way you can do it, and I'll be okay with that. If that's your argument, you realize it's unimodal and it's relatively symmetric. So I wouldn't argue that point there. It's definitely robust to this violation because the data itself looks relatively normal. The other way you can do that is to actually calculate the descriptive statistics using descriptives. Okay? In this case, I want descriptives on diff. All right, and I want nope, I don't actually want descriptives. What I want is the kurtosis and the skewness, so I'll need to use explore. So analyze, descriptives, explore. Okay. I want diff as my dependent, and statistics is okay, and options is okay, and I still don't have the right thing. I just want frequency. So analyze, descriptives, frequency, diff, stats. There we go. I want skewness and kurtosis. and I want mean median mode, and click OK or continue, and I don't want the frequency table, and just click OK. Okay. Now, what I got back is the mean median mode, skewness, and kurtosis. Right? The mean is a little bit larger than the median, but the median and the mode are the same. So the reason why the mean is a little bit larger is because I have that missing blank next to 2 down here. You know, this missing blank here tends to pull this slightly out. Otherwise, the mean would equal the median, which equals the mode. So you can say with, you know, it's not that far off from saying that it's normally distributed, because it, relatively speaking, mean, median, and mode are pretty much aligned up together. On the other hand, another way you can look at this is if the kurtosis is close to 1 and the skewness is close to 0, then we could argue that the data is relatively normal. Okay? The kurtosis is close to 1 in absolute value, and the skewness isn't that close to 0, but you know, it's kind of skewed. Clearly, it's kind of positively skewed. So again, you kind of have some argument that it is normal, some argument it's not normal. Another way you can do it is to go to QQ plot, okay, which you can go to Analyze, Descriptive Statistics, QQ plot, and plot that variable. And the distribution here is normal, diff, okay, and just look at what it looks like. If it's normal, it'll line up on this line. If you see some deviations from the line, then it's probably not normal. Sorry, had to kill a mosquito. Okay? And when you look at the graph here, it kind of looks like it's on a line. It kind of little deviations from the line, kind of goes up a little and down a little. So again, it still seems to suggest that it could be normal. Okay? So all of these visual cues kind of let you know that if it's not normal, it's not that bad, because clearly it looks relatively close. Okay? But we do have a way to actually calculate a test to determine whether or not it's normal. And that's called the KS test, or the Shapiro-Wilks test. KS stands for Kolmogorov-Smirnov test, named for the 2 Russians who found it out. And the other one is Shapiro-Wilk, named for the other 2 people who found out that test. So to calculate those, you have to go to Analyze, Descriptive Statistics, and I'm not sure, let's see, it's not this one. It's Explore. Analyze, Descriptive Statistics, Explore. Okay. And we put diff again in our dependent list. Okay. And here we're going to click on plots. Make sure this check here is checked. Normality plots with tests. Everything else is okay. Take a quick look in stats. Alright, give me the confidence interval. That's fine. Also, give me the outliers. Why not? Okay. And click continue. And click OK. Okay. So we go down to the bottom. What we have is the 95% confidence interval of the mean. We'll talk about that in a minute. Okay. We had, again, the skewness and kurtosis were given to us. Okay. But the thing that I want to show you is, are there any extreme values? Okay. And so you see, there aren't really any extreme values. Okay. So we're good there. And we'll keep going down. Here is your Kolmogorov-Smirnov test. Okay. The test of normality, the null hypothesis is that it's normal, and the alternate is that it's not normal. So what you want to find is that the significance level, which is the p-value, is greater than 0.05. You don't want to reject the null hypothesis. Okay? But the Kolmogorov-Smirnov test, or the KS test, is known to be biased on small samples. In this case, small is less than 50. We only have 8 things here, right? So we don't want to use the KS test. We want to use the Shapiro-Wilk test. Okay? Same argument. The assumption is that it's normal, and if we have something that's greater than 0.05 in the significance level, then we say, fine, it's normal. Notice the significance is 0.542, which is much greater than any commonly used alpha like 0.05. So we can say it's normal. We don't have any proof to suggest it's not. And we can continue going forward. So that's how you go through your 4 tests to make sure that in fact you should be using the t-test. Is it continuous? Am I looking at numbers? Yeah. Do I have 2 groups? Yeah. Are there any outliers? No. Okay. Is the difference looks relatively normal? Yes. But even if it doesn't, I should still be okay. All right. Let's actually run the tests. Okay. So the next thing you have to do, go back to your data set. Okay. Remember, I have Thursday and Friday. To run the paired sample t-test, you tell the SPSS to go to the paired sample t-test. So you got to analyze, compare means, because that's what we're doing. Not the one sample t-test, not the independent sample t-test, not the one-way ANOVA, the paired samples t-test. Click it. Okay. Here you have a box that says, tell me what my paired values are. Now, SPSS is going to do variable 1 minus variable 2. So if you want to have a positive t-value, or you want to actually look at final minus initial, make sure you put the last one in variable 1. I know it's counterintuitive. And put the first one in variable 2. Now it's looking at final minus initial. Okay. Options? Sure. Give me the 95% confidence interval. Why not? And that's it. That is it. That's the whole test. That's it. That's it. That's it. When I click OK, boop, I'm done. What does it tell me? It tells me in the paired sample statistic, this is what my mean was for Friday, 69.88. This is what my mean was for Thursday, 68.13. So at first glance, it looks like it was a 1.5 difference or so, right? They even give you a correlation, which interestingly enough is pretty close to 0. They're not really correlated. And you can see from that significance level that they're not correlated. But the important thing here is the difference. So we see that on average, the difference of the mean difference is 1.75. So that means that on average, the golfers had 1.75 more strokes on Friday than they did on Thursday. But the question is that large enough? Okay. To figure that out, we have to look at the confidence interval or the actual t-test. Okay. So this is telling you the t statistic, 2.411, with n minus 1 degrees of freedom. Here we have 8 pairs, so 8 minus 1 is 7. Gives us a p-value of 0.047. Okay. If you remember the question, it said at 0.05, if I'm not mistaken, is there evidence to suggest this? The answer is yes. Why? Because I do not have 0.05. It's not 0.05 or more. So since this is less than 0.047, we conclude that there is in fact a statistically significant difference in those things, which means that Friday's score is in fact larger than Thursday's score. Now, if you remember the setup, the assumption is that the mean difference is 0, and the alternate is that the mean difference is not 0. So if 0 is included in the confidence interval, I again would fail to reject my null hypothesis. So look at the confidence interval. This will be calculated with d bar plus or minus that t-value, 2.411, times the standard deviation, which is 2.043, divided by the square root of 8. That number is going to give you 0.034 on the lower level and 3.466 at the top level. 0 is not in here. In fact, it's out here just barely. So we conclude that there was, in fact, a statistically significant increase. You can see that with the confidence interval, you can see it's increased. With the actual t-test, you can't. Remember, we just know that it's not the same. Okay? And that would be your conclusion. Since t, which is equal to 2.411, actually, I don't even have the critical value to compare that to. So we could say, since the significance value, the p-value, which is 0.047, is less than the significance level, which is 0.05, we conclude that there is a difference in the Thursday and Friday scores. And by looking at the confidence interval, we can see that the scores increase slightly on Friday. Okay? There's an example of a t-test paired with SPSS. I have one more for you. Okay? Here's question number 2. In an effort to improve the mathematical skills of 10 students, a teacher provides a weekly 1-hour tutoring session for the students. A pre-test is given before the session, and a post-test is given after. The results are shown here. At alpha is equal to 0.01, can it be concluded that the sessions help to improve the students' mathematical skills. Now here, if we're talking about a help in scoring, we would want to know if the scores on the test have increased. So this is a one-sample t-test. Okay? Now the p-value is going to give you the p-value for a 2-sample t-test. If you want to know the value for the 1 sample, divide it by 2. And there you go. Okay? So here's your data on 10 students. It's the same students. So how much they did differently, you can compare 88 to 82, 80 to 76, etc., etc., etc. Okay? So let's take these data points and plug them in SPSS and do it. Okay? So I think, if I'm not mistaken, I got them already. Sweet. Okay? First question is this. Is the data continuous? This is points on a score, on a grade. So yes, they're continuous, range from 0 to 100. Categorical groups, I got 2 groups. I have a pre-test and a post-test. No more, no less. Good. Are there significant outliers in the difference? I don't know. I didn't calculate the difference. I have to do that first. So we go to transform, compute variable, and I'm going to call it diff again. And I want, in this case, post-test minus pre-test. Okay. Boop. Got my difference scores. I'm going to take off my decimals for the difference score. Now, I need to know if, in fact, there are any outliers. So I'll go to Analyze, Descriptives, check on Standardize for my differences. If I see anything greater than 3, I'm going to have a trouble. I clicked it, go back to my original data. I have a 2.3 here. That's pretty large, but it's not outside of the realm of possibility. So we'll leave it there. No problems with outliers. Last, is it normally distributed? I'll look at the KS test or the Shapiro-Wilk test. I only have 10 values, so I'm going to read off the Shapiro-Wilk test. So Analyze, Descriptives, Explore, diff, independent list, plots. Give me the normal plot. I don't really care about the normal plot, but I care about the tests. Continue, and okay. Let's give me the plots. Okay. So it's telling you the minimum difference was -1, the maximum difference was 18, with an average difference of 6.5, and a standard deviation of 4.927. So if I were creating my t statistic, it would be 6.5, which is my mean difference for the sample, minus 0, because that's my hypothesized difference of 0, over the standard deviation, which is 4.927, divided by the square root of 10. That would give me a t statistic value of something, because I haven't done it yet. But it'll show you when we do the actual test. Okay. In the meantime, look at your normality. Notice that the significance is greater than 0.05, so we don't have any evidence to suggest it's not normal. So now I can do my test, and remember, we already have all this information. The 6.5 minus 0 over 4.927 over the square root of 10 will give me some t statistic. So we go to Analyze, Compare Means, still a paired sample t-test, post-test. I actually want post-test in the variable 1. I want pre-test in the variable 2 because I want it to be positive. Okay. And okay. So now you can see that the standard error of the mean is 1.558, which is 4.927 over the square root of 10, right? So you'd have 6.5 minus 0 over 1.558, and you'd get 4.172. Now you have this with 9 degrees of freedom, and you look at 0.01 is two-tailed, so for the one-tailed, it needs to be less than 0.005, right? And so when I look at this, I have 0.001. It's still less than what I need for a one-tailed test. Okay? So I would reject it and say there is evidence to suggest that the tutoring session worked. On average, scores increased by 6.5 points. However, it's likely that the increase could be anything as low as 2.9 points up to 10 points. And that's it. Okay? There is your test. Remember, check. Is it continuous? Yes. Is it categorical? Groups? Yes. Do you have any outliers? No. Is it approximately normal? Yes. Okay. Well, let me go to my analyze. I'm going to my compare means. Let me put the second one in first under paired sample t-test. Put the first one in second. Click OK. And read off my t-score or my p-value. Compare it to my significance level to make my determination, just like we did all class long with the one sample t-test. Okay? That's it, guys. Have a good day. Talk to you soon.